Okay, here we go. And welcome to Display Data.
Hey everybody, and welcome to a fuzzy, furry, and clawy desk of Lady Ada. It's me, MOSFET, the cat, and I'm going to stand in for Lady Ada, and I'm going to eat all the tuna fish and be really annoying. You're such a good cat, MOSFET. You can sit on my shoulder. So me and MOSFET are going to have we're going to have another desk of Lady Ada tonight. It's going to be kind of an update of the stuff I've been working on lately. The last stream we did was about using a Raspberry Pi as a native GPIO OpenOCD programmer, and that would let you program chips like the SMD21, which is I'm working a lot with, and the NRF51822, which is the Bluetooth Cortex M0. So we covered all of that stuff on how to configure OpenOCD and get it compiled, and I played some more with it today and actually started kind of modifying the testers that I'd already designed that normally would use something like a J-Link or an ST-Link to instead use the native GPIO on a Raspberry Pi. Turns out that actually the chip I'm using, it doesn't like the native GPIO. I use Sisyphus GPIO, which makes me think there's some timing offset thing I have to figure out. It's too fast if I use the native GPIO, but if I use the Sisyphus, the file system GPIO, works great. So it is a little bit slower, but I think I can speed that up with a little bit of effort. Got it running on a Pi 2, and so let's check it out, and you can see kind of how I took the code that we were working on yesterday and pulled it into a full tester.
Okay, what do you want to get to first?
Let's go to the hovercam. So here is my prototyping plate for the Raspberry Pi. Get that ready. So this is a Pi 2, and I just have it mounted here. And I was doing some, before I had the wires going from here, I had these little jumper wires that went from the GPIO header to a SWD, a 2x5 breakout. This time, because I want to make this a standalone tester, I started saying, okay, well, let's put a Pi TFT on there because that'll help me get ready to kind of isolate it. So you wouldn't use a computer to log in or an HDMI display. You would actually just use the TFT itself, and then maybe have a clamp, or maybe it would be an OLED in the end. I'm still kind of working that out. And then there's an SD card. And the SD card, I worked on, what I pretty much did today was I took a copy of Jessie Lite. They just released a new version, so I took the 318 Jessie Lite, and I customized it. And I'll show a list of all the things I did. I basically installed all the software I thought I would need, like Avahi and OpenOCD and AdaLink, and we've even got J-Link drivers for ARM. Turns out they actually have released Raspberry Pi compatible J-Link driver code, so that's cool. I'm going to use it for the NRF51822 because it's a little more stable. And just a bunch of other stuff, and PyTFT code, of course, and Python, and NetAtalk. Basically all these things that you would need to get your Pi in a good state, because I want to be able to basically duplicate this card for every PID, every product we make, and just tweak a few little things so that it's pretty much out of the box, ready to go. I just dump the new tester Python script in there, dupe the card, and then I put it in the boot directory as well. I'll show that all. So here's the Pi, and I'm going to plug in a keyboard just in case I need to use it. So luckily I got a whole bunch of USB ports. So we've got Wi-Fi, and I'll connect to it over Wi-Fi. And then I've got this USB port here. And I'm going to I didn't finish the full pinout test, so there's no pogo bed for this. I'm skipping over that part because I know that part really well. So I'm just connecting to this Metro M0, which has an SMD21, so it's a prototype. And then over here, I wired up the SWD breakout, and instead of putting headers in and plugging into a breakout board, I just used some silicone wires. I connected up ground, SWD IO, and SWD clock. I didn't connect reset because it's not working with Raspberry Pi native. I'm not sure exactly what's up, and I was like, I'll just let it be. And figured, you don't need it it turns out, for this chip. So then plug in the SWD cable into your device and plug the other end into here. And so the cycle will be, for every time you have to test a new device, you'll have to plug in this cable, which is not too bad. Plug in the micro USB, and then there'll be like a bed of nails tester like this, where it'll clamp down, and that'll test the GPIO. But we're gonna skip that for now, just because I want to get the programming good. The self GPIO test is like super easy. I do that all the time. Okay, and then we're gonna power up the Pi. And what's nice is Jessie Light boots like super fast. So assuming this didn't die in the 5 minutes, it'll boot up. So we got it on the Pi TFT. And it's just going to scroll by its thing for like a half a minute or so. And then it will boot into the shell. And I'm going to get real close so you can see what is going on in the shell command. Okay, do you think that's readable?
Yeah, I can zoom into it.
Okay, so it booted up and it completed booting, and it says waiting for button number 17. And so we've got these like handy GPIO buttons down here, right? So what you can do is, in my Python code, I use the GPIO Python library to pull for that button. I just have it on a pull up and I wait for it. And then when you press the button, it will use OpenOCD to program the chip on this board. And it actually takes about 20 seconds. I'm going to try to speed this up. This is the part that's a little slow because it uses Sisyphus, not native. And then it programs it. It looks for the COM port that's generated. It opens the COM port. It's actually supposed to look for the GPIO test, so I put meme fix me here so I remember, like, hey, this doesn't go into production. I have to fix that. But I faked it. I just kind of skipped out of that test and said, okay, the test is okay. Then it kicks the bootloader off. So this is the COM port for the bootloader, and it runs BOSAC. And then if BOSAC returns properly and has all the right strings, it'll say passed, time elapsed. So let's say I do something like I unplug the SWD cable, right? So this is a demo of what it would look like if it was failing. So this time it says, okay, waiting for button 17, you press it, and it's gonna try to program, and it's gonna like immediately see failed. Like it prints out some things that couldn't initialize a debug port, but pretty much it tells you like, hey, this didn't pass, check a couple things. If I feel like it, I'll add hints, but when we have 99% yield for most things, or like 97 to 99, so it's like spending a lot of time on like having every error is not as useful, because it's usually not a cable's not plugged in, it's usually like a shorted pin, and it's hard to detect a shorted pin. Like it's hard to know when a shorted pin is gonna cause an error, because depending on what's shorted, it could fail at programming, it could fail at USB detection, it could fail at the GPIO test. And then at the end, it has this little blinking LED. So the next possible thing is, okay, let's say we unplug USB. So this time we run test, and it does manage to program. Oh wait, it does not. That's because I know why. It's actually not supposed to be powerable. Let's see. No, it still fails. Yeah, it's not even supposed to be working. Sometimes it can. The SWD and SWC pins actually can power the chip enough. Let's say I power it from, so let's like plug in this power adapter, for example. Okay, so now it's powered, but there's no USB. And run the test again. So it should complete the test of programming, but when it actually gets to like the numeration part, it'll like flip out. So programming, okay, but yeah, it's like, no ports found. It's a null set. Didn't enumerate USB. So it gives you a little bit of a hint, like, okay, I failed at that point, and it prints out a failed notice. So the idea is that, getting this cycle time really short, and also making it really easy. Like if all you have to do is plug in USB, and then even for something like the Feather, you don't have to plug in an SWD cable because the SWD pins are on the bottom. So you just plug in the micro USB and clamp it down with the clamp and go. So what's nice about this is that you just press that button and like it's pretty much just does its thing. At the end it tells you about how long it took to test. So I think this test is like 20 seconds, which is okay, but I think I can get it down to like 10 or 15, which I would prefer. So I'll probably work on getting that programming step to be a little bit faster. Right now I program the bootloader and the test at the same time, but since SWD is slow, what I might do is program in the bootloader and then use BOSAC to load in the test. So like I use USB to load in the test software instead of using SWD. It's kind of like a trade-off. Like at which points do you use the bootloader to do stuff? At which points do you do native programming? But I take 17 and a half seconds. It's not so bad per cycle. That's pretty good. But yeah, I think I can speed that up a little bit. And I like to do that because again, when you're making thousands, 10 seconds counts. So that's that. And I thought I could show the Nordic version of this tester, or I could kind of go through the code. What do you think would be more interesting?
Well, I think showing the code from this one, since folks saw it in action, the Nordic one isn't ready yet, so.
I did get it working, but with the J-Link.
The J-Link.
Well, but maybe I'll show that tomorrow, and we'll just since I got this working.
Yeah. Maybe show a little code on how this is working behind the scenes. So
sure. Let's go to the compy. Thanks, little tester. It's just going to sit there and wait forever. So this is the I rebooted. So let me restart my session.
Do you want me to zoom in on this terminal?
Yeah, I will.
Okay. Tell me when you're done with resizing it.
Yeah,
You're done?
Yeah, that's cool. Ooh, man, I got the little overlay in the corner. I can make it shorter. You want me to make it?
No, that's okay. I'm gonna get rid of the overlay.
Okay, sweet. So when I logged in, it actually jumped right to that code. That's because in my profile, at the very end, I tell it, okay, CD boot. I just did that to make it a little faster because I was doing a lot of stuff in boot. I might eventually have it kick the Wi-Fi, but so far the Wi-Fi is actually pretty stable, so I don't need to do that, so I commented that out. I don't really need this because I'm not going to be doing, I'm only doing console, but let's say I wanted to run X or 11 or something, will show up on the PyTFT, and then I tell it, okay, run boot/test.shell. So the reason I do that and not run the command for the tester itself, I say, hey, go to boot.test, and then if you go and look at boot.test, it's actually the thing that CDs into the directory and then runs sudo python featherm0 basic.py, which is the tester. And the reason I do it that way is because the boot directory is readable by plugging in the card into a computer. So if I want to change the code or change the configuration or like something needs to be tweaked, we don't have to like boot the Pi up and like wget. You can just drag files onto the boot directory using any Windows or Mac computer. It's much more convenient. And you'll also be able to, I'll be able to basically train people at Adafruit, like, hey, if you want to make a tester, take my empty image that won't have any files, drag the folder in, and then edit this line to tell it which directory to go into and then what Python script to run or what shell script or Ruby or whatever to run. So that way it's a little bit easier for people to configure because like once the Linux machine's running, it's pretty simple. It just says press button 17, but for beginners, getting them to boot into a Pi and then you have to SSH in, it can be a little challenging. And I want to make this easy for everybody who might have to maintain this in the future. So in boot, I have a folder called testing. And in testing, I actually have two testers right now, but I'll go to 2772. And this is the tester that I just talked about. So it's a couple things in it. It has blink.bin. This is just when it's completely done, it burns in blink, just blinks LED on and off. BOSAC Linux, this is an ARM version of BOSAC, so you can use that to upload code through the bootloader for the ARM Cortex M0. FeatherM0 Basic PY, this is kind of the mistress of testing. This does all the actual work. FeatherM0 bootloader and then a date. So this is just the bootloader hex file as of March 5th. So I actually made a couple tweaks to the bootloader, and so this is the latest version. This is an all-in-one version. So this contains both the test code and the bootloader. OpenOCD config. This is just kind of handy. Like I don't actually use this. I put it on the command line, but this in case I ever need to manually do some tests, I can just run OpenOCD, so it makes it a little handy for me. And then the config files for Raspberry Pi native and Sisyphus GPIO native on the Raspberry Pi. So this is where I get to define which pins are the SWDIO and SWD clock pins. So if I have to by chance change this, or for whatever reason, it's very easy. You just go here and you just change what pins those are. And this is all on Git. So this is where I try to have all of the tester files like on GitHub in a private repository, so that if I ever I don't think it hasn't happened lately, but if I was working on it and the SD card got destroyed, I would at least have the most recent backup. And this way it's not stored on my hard drive, it's stored like in the cloud. So kind of like that. And there's a README. The README will eventually have instructions and stuff, but I just finished it 5 minutes ago. And then let's look at the code itself. So this is the tester. And so this is that, the GitHub repository. Oh, can you go?
Oh, sorry.
Sorry, I
Tuned up
forgot.
for 1 second.
Yeah, no, look, it's stuff going on.
Oh, that's not what I wanted.
Ooh.
Why did I do that? I want to zoom out of here, right?
Okay,
I've never seen that before.
that's cool.
Weird.
Weird.
So this is the whole screen, right?
Yeah.
You want to show the whole screen?
Yeah, that's cool. That's great. Thank you. Zoom. Okay, so this is that repository. So you can see I've been working on it the last couple hours, on and off, just getting it nailed down. And then let's look at the script that I'm running that actually is doing all the work. So
Let me go back to this. Oh, wait. No, I know why, because that's, okay, I know what's going on.
yeah, I can just make this text bigger. Okay, so start with, import all this stuff. Half this stuff isn't probably even used, but whatever. This is the button that's going to be used to basically to get the test running. And if you look at the very bottom, there is main. So, there's a verbose flag, and if you have other flags, it sets the pin to be a pull-up input. It keeps track of the time. Actually, this turns out this line isn't necessary, but so while true, it says, hey, I'm waiting for you to press the button. While the button is, wait for it to be pressed, wait for it to be released, keep track of what time it is, and then run the test. If the test passes, print out passed in green and print out how much time it's taken. Otherwise, print failed. And then, so now we have to go back up to run test. So run test basically just runs a bunch of commands using Python subprocesses and just pipes the output. And just every program has its own super weird ass way of handling output. It's not as bad as Windows, which I've determined has 3 or 4 different ways to get stuff onto the console or the screen. Just text, not even graphics. But with Linux, sometimes you have std error, sometimes you have std out, and sometimes things hang, and sometimes there's delays, whatever. So using the subprocess popen is kind of nice because you can have a timeout, there's a process wait, but you can also, I'm pretty sure popen has timeout stuff. I don't need it for this because none of these programs hang, they all exit, but once in a while I've had programs I have to call that if they're getting a bad state, they don't return. So it's something to watch out for. So this just calls, so it starts off with, okay, what are the starting serial ports? This is useful mostly on Mac and Windows because the ports enumerate and appear and disappear. And this auto detects which is the new port that's shown up. For Windows, for Linux, it doesn't really matter because it always shows up as TTY-ACA or ACM0. So it calls OpenOCD, which we worked on yesterday with the Sisyphus GPIO config. Again, if I want to change this, it's really easy. Transport select, SWD, adapter select, source at SAM91 config, init, targets, reset, chip erase, sleep 500 milliseconds, bootloader 0, program the hex file, verify, reset, shutdown. So that basically connects to the chip, erases it, waits a little bit, turns off the bootloader protection, programs in the bootloader. I'll add in bootloader protection later, although all the Arduino zeros that go out right now don't, so I don't know, maybe it doesn't really matter. And then it just waits for the output, and then it looks for the output. If the return code, because you know all shell programs return 0 on success and any other number for failure, which is kind of the opposite of how a lot of people think of stuff. You look for the return code, which comes from the process wait. If it's not equal to 0, that means there's a failure. Print what did occur, because that's kind of handy, like what was the output from the command, and return false. And then that main loop will print out failed. And then what you do is you look for these lines. So like I basically just look at the output and look for making sure that the output has these like important lines that appear. That's kind of, you know, it's good to look at the code, but you also want to look at, you know, did it actually do the things you wanted? I mean, it would fail later in the test, but it's fast to know early. So reset line, that tells me that did it find the chip? Like was the chip found and reset? So if it prints out @samd CPU target state halted, that means it succeeded. If it prints out target state unknown, it means it couldn't, so that would not be found. Erase line, chip erased. It's pretty simple. If OpenOCD finds a chip and erases it, it will print out chip erased. Program line, so this depends on the program, but basically you want to look for, did it verify the entire size of the code? And this is also a protection against if I change the firmware, if there's a firmware revision, this number will almost certainly change, so I just have to keep those in sync. And that's actually kind of useful because it makes sure that I don't accidentally write old firmware. Like I have to, if you have to keep the firmware and the program in sync, it's a little bit easier to avoid, oh shoot, like I programmed in last year's firmware by accident, or we overwrote it, you know, because it isn't date coded or something. So go back to erase line. Okay, so, but if it did reset, it did erase, it did program, then it's good to go, so you can continue on, it says program. Now you wait for USB enumeration, 2 seconds, and you say, I have a little helper above that basically lists all the USB ports, and if it doesn't find a USB port, it says, hey, something went wrong, but if it did, you can open up that USB port, connect at 115 kilobaud with a 1 second read timeout, unless it totally failed to read the serial port for some reason, in which case you should totally bail. And then while true, so you know, forever basically. I mean, they can add a timeout, but again, I've never really needed it. It reads a line, and then it prints out the line, and then it looks for the output test okay. And then if so, it says, okay, test passed, break. And then that basically was the GPIO self-test. So the Raspberry Pi doesn't test the GPIO. All it does is program the chip and the bootloader and all that good stuff. And then it connects, and the M0 itself does its own self-test. Because it should. It's like, it's really good at like testing analog voltages and digital pins. So it can twiddle all its pins to know whether things are shorted or not. And you just have to construct the tester so it would detect bridged pins. But I've been doing it for long enough that I've got a pretty good system for that. Then you reset by closing the serial port, reopening it at 1200 baud, which is like a little bit of a kickoff signal. It tells the user program that, hey, I want to go to the bootloader. And I have to make sure that this works, otherwise it means that the bootloader detection code isn't working well. Just waits a second, closes the port, waits another 2 seconds for enumeration, does that serial port detection thing to find the bootloader port. And then I have a little thing here that just sort of, you know, depending on what platform you're using, Windows, Mac, or Linux, it runs a different program. It's just been compiled for like every platform. And then I just use this in the subprocess command. So the same thing, it's like, you know, BOSAC, and it says like, you know, info, debug, you know, don't auto-detect ports, erase, I don't know what W stands for, verify, maybe write firmware verify, blink, there's the blink, and then reset. Run that, make sure that it returns 0, so okay, I was able to talk to the chip. And then again, I'm looking for that special line that it was able to verify and program the right amount of flash. And then if it got to this, I'm actually like, you're pretty much good to go, you're done. You've tested everything that's worth testing. And then the person who's doing the test actually looks for the blinking LED, and that's like the visual part of the test. And that's pretty much it. So it's just about like testing everything that's exposed, doing it really fast, but making sure you have as much coverage as possible for, like this isn't going to test, like if there's a missing 0.1 microfarad capacitor, it will still pass test. It's just one of those things we don't do an optical inspection because it takes much too long and we rarely have missing capacitors. But this will basically test all the functionality. Like it enumerates as a device, you can connect to it, you can bootload to it. And so now I have a standalone tester so that this will be able to, I think once it's tweaked, be able to probably do an entire test in about 10 seconds, which is really great because it means we can program and manufacture about 2 or 3 times as many as we are now. Because I think right now we're doing about 30-second with a Mac laptop. We use a Mac laptop to do the J-Link connectivity and the Mac USB port, which is also a little risky because if there is like a really terrible bridge, you could, in theory, have you could not short out and like permanently damage your USB port, but it would set off the fuses inside of it, and it's kind of annoying. This is kind of nice. It's like it's a Raspberry Pi. You just get another one if anything ever happened to it. And that's my tester. Isn't it lovely? Maybe I'll press this button again. Yes.
One of the neat things about this too is if you're a company like us where we're growing, we have 20 or 30 people in the fabrication department, what do you do if you only use those really expensive testers that are like $5,000 each? You have it's a cost every time you want to test more and do more.
Oh yeah, like with this, the total cost of a tester is, it's about like 2 hours of work to build it. We're gonna make it'll make a nice acrylic thing and like a clamp, and it'll be like a little bit fancy, but it's still like laser cut stuff. Parts that we already have in the store, like we have all these cables and adapters and the Pi TFT and the Raspberry Pi and SD cards is stuff that we already stock, so that's kind of handy. Just go downstairs and pick it up, or upstairs and pick it up, and then if we need to make more of these, it's like maybe $50 in parts or $60. It's like it's under $100 in parts, which is what really counts. And again, like I love these J-Links. These are like amazing, but they're $500. So I can, for that price, I can make 5 of these testers, and they're compact and they'll be all in one. Oh, and I can show off what the tester's going to look like. Do you want to go to the computer again real fast?
Yeah.
Let me. This kind of puts everything in a weird spot. So, hold on, I got a lot of testers I've designed. 277. Oh, is it?
Do you remember what the first tester you built was? Probably programming a VR chip, so it was probably like a...
It was probably...
Well, no, maybe the Zoxbox.
It was the Zoxbox I/O tester.
Yeah, I remember that one.
Yeah, that was horrible. I still have it.
Yeah, we still have it. It is the Zoxbox tester. It was for those big chips.
Okay, so this is the design for like a hat that would do testing for the M0. I actually put in pogos in case I can get this also working with BLE programming, but I've actually had somewhat mediocre luck with the OpenOCD and the NRF 51822. Like it kind of, I actually, it's interesting, like I did get the M0 to work super solidly by using the Sisyphus GPIO instead of native, so I'm going to go back and maybe try the NRF 51822 that way too. But this tester can basically test the M0 basic, the M0 ADA logger, which just like adds a self-test to read for the SD card. It can also maybe do the Bluefruit. It'll be able to do like the future like RF M0s and stuff. So I'll be able to probably reuse this hat a little bit, but this will have like a clamp that will hold this down. So these are going to be pogo pins here, and it'll be clamped down. And you can see there's like a bunch of components. There's like a resistor divider that goes to A0. So this is reads the analog voltage to test the chip, and then these pins are connected together because it's used to test that you have full GPIO. Like one is pulled high, and then the other one is red, and the other one is pulled low, and then you basically read the opposite to make sure that the pins are connected or not connected the way they should be. And it's just important just to pick ones that aren't on the chip. They aren't next to each other. So it's okay if they're next to each other on the header. They just can't be next to each other when they get to the QFN, because that's where you're going to get bridges. and there's a reset button, or like not reset, the like kind of activate button. So you press this button to start the test, and then I put an OLED breakout here because I think I'll be able to adapt the print. Like there's not a lot of printing that has to go on here. I think once I get it pretty solid, I will just have it print out like pass or fail pretty much, and like maybe one little hint about what it could be using our Python OLED code that Tony deported to Python. So this makes it very compact. It will fit on an A+, and then you just plug in the USB into the USB, the USB for the M0 into the USB port, and you're pretty much done. So that's kind of an idea. I mean, like I don't know if this is going to work out. I might need to stick with the PyTFT, but if I get it fast enough, and it seems like if it, I'll probably do a run where we test like 200 or 500 Feather M0s using like this kind of PyTFT with a separate clampy thing. And if like I don't hear any issues, I'll move to a full standalone, like all-in-one with the OLED.
Oh, okay.
That's the plan.
Good work.
Okay.
All right,
Well, we don't know if
that's
this can work, but I'll get prototypes and I'll test it.
Yeah. Okay. Well, that's everything for tonight.
Okay,
Thank you,
great.
everyone. We'll be broadcasting probably sometime over the weekend, and we hope you enjoyed this kind of glimpse into modern manufacturing.
This week has been tester-a-palooza. I actually took a little bit of break from new products just to I wanted to go back and do refresh because the feathers were they're just so popular that I'm like, okay, I have to do a little bit of work to maybe optimize.
Yeah. Yeah, I mean, one of the transitions from a smaller company to a larger company is when you have popularity in products, like Feather that you design, and the demand is really high, the tester is as important as the actual product. Being able to test.
Oh yeah, no, I gotta test a lot.
Yeah, I remember it was like, well, first design like a kit, then it was design something that could be crudely manufactured in a very small pick and place in a toaster oven, and then it was designed for manufacturing in a more optimized process. Then it was designed for manufacturing on really good equipment like we have now, and then it's adding bits of machinery to it like a stenciler and a board loader and a conveyor and all that, and a grate oven. And then eventually it's, it doesn't really matter how good you are at manufacturing, you also have to be really good at testing.
Yeah.
And that's the next round of challenges for companies. And one of the reasons that we're doing these shows is because, first off, no one is ever going to do shows like this talking about their manufacturing process. This is the secret sauce that everyone is so scared to talk about and share.
You know, it's funny. Only Megan Smith was like, she was like, hey, wait a minute. You actually have to design 2 products for every product, the tester and the product. And actually, by the way, like the tester often takes a little longer.
Yeah, we had the CTO of the US, Megan Smith, visit, and she was, I think, the first visitor, maybe besides Bunny, who actually picked up the hardware and could talk about and know what it was, and then ask really good questions, and then make really big observations about probably what we're working on and what we're doing. It was neat. Like, there's a reason she's the CTO of the US.
Yeah, no, she's pretty cool. She's a Mechie, and she's just like, this is cool. And
Yeah.
I'm like, yay. Yeah, and she started to analyze how we were doing so. It was kind of neat. It was
she was
watch the video.
the second female engineer on the cover of Wired. Second, you were the first. So I think it's neat because I always imagine the sheer volume of Samsung's Android phones that they make a day, and the sheer volume of iPhones, something like 5 a second or some crazy amount.
I can't even. I would love to see the test jigs. I mean, the thing is that they're building. It's not like one day somebody shows up and it's like, okay, you have designed the Android tester. It's not like that. They have 7 years worth of incremental tester design improvement.
I'm sure they have testers to testers.
Well, you have the gold.
Yeah, but no, they have to testers.
Probably.
Because they probably manufacture testers. They make testers.
Oh, yeah, they probably manufacture the, I mean, you have to make thousands.
Yeah. Okay, so we'll be around this weekend. Thank you, everyone.
Yay!
We'll be broadcasting live in some way, and we'll work on a new show that we may or may not broadcast tomorrow with Colin.
Ooh, I think we had 3 streams today.
There were 3 streams today. All right.
Data for TV.
Pick up some electronics.
Pick up a Pi TFT, and SWD cable, and make your own. I mean, like, hey,
Yeah.
if you're, I know that there's probably a half a dozen people watching this that are working on their own at SAMD, Kickstarter-based projects, whatever. I just kind of did all the work for you. Like, this makes it easy to make a lot.
Yeah. Okay.
So
All right, folks.
use the knowledge.
All right. See you soon. Bye-bye.
Bye.